So as you see in the book, there is a proposed assembler implementation with actually rather detailed description of the functions that one need to implement. The assembler can be implemented in any high-level language. Here we suggest to use Python. The design should look like this. The assembler should have an input file, the assembly code, and should produce an output file, which is the hack machine language code. We have 4 main software modules. The parser that looks at each instruction and finds its underlying fields. Code that translates each field into the corresponding binary value and assembles the resulting values into the machine language instruction. Symbol table module will manage the symbol table, and then we have a main module that initializes the entire process, drives the 2 passes, and processes the code from instruction to instruction. To simplify the coding, we suggest that you implement the assembler in 2 steps. First, build an assembler that can process programs without symbols. It means that the first pass is not needed, and actually the entire symbol table handling is not needed. Then in the second stage, extend the code to have 2 passes and be able to handle symbols. So let's look a little bit at the modules one by one, and we start with the parser module. So the parser module will be called for each instruction, for A instruction, C instruction, and then we find a label declaration. And looks for the components of the instruction, right? Find the symbol, find destination, find computation, find jump. Note that for this, the parser needs to know the exact syntax of the assembly language. Okay, what kind of routines do we need in a parser module? Of course, we have to advance in the program. We have to be able to figure out what kind of instruction we have, A, C, or label declaration. And then for each command, we have to define what kind of fields do we find in the command, right? In the A instruction, we can find symbols. In the label declaration, we can find symbols as well. In C instruction, we can find destination, computation, or jump. Code module. Right, the code module will be called for each instruction after the parsing step, and it simply has to find the binary representation for the components of the instruction, right? These components have been found in the parsing step. Simply put them together then into a binary instruction. And so if it's an A instruction, it's simply starting with a 0 and then the binary value following it. For the C instruction, it's starting with 111, and then the 3 bits for the destination, the 7 bits for the computation, and the 3 bits for the jump has to be filled in. Okay, finally the symbol table module. It will be called at the initialization part of the program, right, to fill in the predefined symbols, and then it will be called every time whenever a symbol appears. It needs to add new labels and variables and has to find already defined labels and variables. what kind of routines do we need here? We need a constructor to create a new symbol table. We need to add entries, which means adding the pairs of a symbol and the address. We need a routine that finds existing entries, and we need a routine that gets the address of the existing entries. Okay, and with this, the main parts of the assembler are actually defined. Let us summarize the objectives of the assembler and in general any translator or compiler. Okay, the objective is to translate the program from one programming language to another programming language. In detail, it means to extract the program semantics from the source program using the syntax rules of this source language and re-express the program semantics in a target language using the syntax rules of that target language. In the case of an assembler, we translate from assembly to machine language. It means translating A instructions, translating C instructions, and handling the symbols defined in the program. In this lecture, we provided a detailed implementation guideline of a possible assembler implementation. We have seen that the assembler process is rather simple. Okay, the reasons are the following. This assembler translates each assembly command into one binary machine instruction. So it can process the program line by line. Variables are 16-bit binary numbers. It means that they require one word in the memory. So memory handling is simple. The program structure is simple. The program is implemented in one file. There are no modules, no functions, no function calling. The symbols, because of this simple structure, are also all global. So once they are defined, they are used in the entire program. So let's see what will be the next steps in the course. Well, we will continue to climb up in the software hierarchy so that finally we reach hardware independent languages and also can allow more advanced programming possibilities, right? Complicated program structure. Actually, we will reach object-oriented languages, introduce complex data types, etc., etc. Okay, specifically, first we will talk about the virtual machine and then define a high-level language which we'll call Jack. Of course, implement the compiler from virtual machine to assembly and from Jack to virtual machine. Then finally we will define our operating system. This ends the lecture on assembler.